Thanks a lot for this short 15 minutes talks that allow to know a lot about everyone. What I first want to mention is that this talk is going to be extremely introductory about random matrices. There will be some other random matrices talks during the week. Tomorrow, two other postdoc talks by Antinos and Kevin Schnelly will come into some more details. And HDO will give a talk for Dyson's birthday on Friday, and it will be much more complete about the field. What I want to talk about is how random matrix statistics are of interest in many distinct fields. And this idea comes back to Wigner, who wanted to understand the energy levels of heavy nuclei, and decided that a good paradigm for it would be an integral model, which is a random matrix as a model for some Hamiltonian. And what is exactly the model by Wigner? It's the following. Imagine you have the set of Hermitian matrices, Hn, n by n matrices that are Hermitian, and you have the Lebesgue measure on it, and you're asking about finding a measure which satisfies the following properties: to be absolutely continuous with respect to Lebesgue, to be invariant by unitary conjugacy, and you also want it to be such that the projection of mu on all coordinates is independent, is a product measure for up to the symmetry condition, which means that on the upper triangle of your matrix, all entries are independent. Okay. So it happens that you have no choice up to a scalar. The only possibility is the so-called Gaussian unitary ensemble. And the entries are Gaussian. So more precisely, we can choose a normalization, which is the following. We take the diagonal entries to be real, and we have an n by n matrix. We normalize by 1 over square root of n. We will see in a minute why. And this is a Gaussian index kk, and the non-diagonal entries is of the same type but complex. And all of these nk and ak prime are independent. Okay, so that's a very specific model, and it happens to be quite integrable in the following sense. If you look at the eigenvectors and eigenvalues for this matrix, they decouple in the following ways. The eigenvectors are uniformly distributed on the unitary group for the Haar measure, and the eigenvalues have an explicit density. Which in that case is exactly the following. Let's call these eigenvalues lambda 1 till lambda n. They are almost surely different. Then the density with respect to Lebesgue is the following. So you see you have a van der Waals square here. And what does this tell us about this spectral measure? So first of all, you can realize that there is a repulsion. It's very unlikely to find two eigenvalues close together. That was a phenomenon that was already identified for heavy nuclei too. And then you may ask two distinct types of questions for this type of model. The first one is the macroscopic asymptotics. What does the whole spectral measure look like in the large n limit? And what you can prove is the following result. If you look at the so-called spectral measure, so the sum of Dirac masses at the energy levels, then it converges weakly to the so-called semicircle distribution. Which means that typically for our choice, it's a distribution we support between -2 and 2. And a typical histogram of such a very large matrix for the eigenvalues will be a semicircle. Okay. So that's for the macroscopic asymptotics. What we refer to when talking about universality, at least in this talk, is about the microscopic asymptotics. The eigenvalues are, okay, let me write a statement in terms of probability and some test function. Maybe it will make it clear what I mean. The lambdas can be negative. They are real eigenvalues. That's okay. So when you look at microscopic asymptotics, it means that you will zoom so that you get just a big O of one number of eigenvalues in the bulk or in the edge. And let me make a distinction between both. So if you make zooming on the edge first, because you have a square root singularity here, the typical gap between the largest eigenvalue and the second largest one will be n to the -2/3. So what you can prove is actually, after when I'm using this ordering, the probability that lambda n -2 over this n to the -2/3, this should be of order 1. Actually, because what is not clear, but it's a fact, is that actually the largest eigenvalue sticks to 2. And this has a non-trivial limit. Which is a function which is called the Traci rhythm distribution depending on t. I don't want to make this distribution explicit. It's actually quite complicated. It's not an analytic function. So it looks like a very arbitrary thing, but what we will see is that it appears in other contexts. If you look at the, so this was for the edge. If you look at the bulk, what you can prove is if you take some number k, which is between some n to the theta, well, say, let's make it simple, and between n over 4 and 3n over 4, somewhere in the bulk, say, no matter where, then you have such a limit, but of course the normalization now is just n instead of n to the 2/3, and n times lambda k plus 1 minus lambda k, which is the distribution of the jump between two successive ones, converges to some quantity, which is called j of t, and j for go down meta, say. Okay. Yes, that's right. So why is this interesting statistics? Let me mention in the next few minutes 2 results about what may be considered as universality. The first type of result is actually there are many other integrable models that exhibit the same statistics. And the range of such integrable models is still a bit unknown, and there are some algebraic reasons for that. On the other hand, there are some non-integrable models for which some analytic tools were developed to prove universality. So I want to give one example of it. One integrable model and it's work by Bike, Deift, and Johansson is about taking a random permutation uniformly for n objects and consider the following problem with the greatest increasing subsequence of this random permutation. Okay, so of course we can get some example. So we get a permutation of n objects. Imagine you take this permutation, and you consider the greatest increasing subsequence. Let's call it k of pi. And in our case, you cannot do better than 3, and it's obtained by 1 to 3. And you may wonder about what is the typical size of this when n goes to infinity, and what are the fluctuations around this typical size. Okay. And what you can prove is that this k of pi is of order 2 square root of n. And the fluctuations are non-trivial and quite unusual in probabilities with an exponent n to the 1/6. This, for any t, has a non-trivial limit, which is exactly this f of t. Okay, I cannot give you any obvious reason for that. There are some algebraic structures, determinantal point processes behind it that justify things, but it's really of algebraic nature. We have no direct bijection or whatever between models.
What's the worst case scenario? It's logarithmic.
Worst case scenario?
Pi, what is the worst possible?
Oh, for the value k of pi, or for
No,
for?
I will give you any permutation.
Yes.
So what is the longest increasing sequence?
You mean with probability you can?
No, not with probability, deterministic. Well, okay, increasing or decreasing?
Yes, increasing or decreasing. So it was proved. I think this 2 square root of n is right. No, I think there is a square root. It was Erdos and Zekeres who have a theorem about it.
Deterministic?
I think it's a constant multiple of square root of n for the worst case scenario. So that's one example. Another example is about more in the spirit of Wigner's typical initial view is if you take a non-integrable model, which is still of random matrix type, is it true that this statistic remain? In particular, do you have the same ones in the bulk in the edge, despite the fact that you don't have an explicit distribution for the eigenvalues? So recent results in the past 5 years or 6 years occurred about it, and what I will mention is a result by Erdos Xiao and collaborators. Is if you take a random matrix of this type, but now you only impose 2 constraints, that all of the entries have a variance of order 1 over n. Okay. But no matter how small C1 is and C2, how large C2 is, and you have a normalization constraint to make sure that you will have the same support for the macroscopic asymptotics, that the sum of these guys for any fixed j is equal to 1. And we still ask independence, absolutely. Then, and self-adjoinness. We keep in the class of Hermitian matrices. Then both results remain, both the edge and the bulk. Okay. So I will not write it exactly. It's exactly this and this remain. And one of the tools towards such a proof proceeds by interpolation between this model of Gaussian matrices and non-Gaussian matrices. And an important tool for this interpolation is a Dyson-Brownian motion that HTIO will talk more about on Friday. I think I will stop here, and as I told you, tomorrow Kevin and Antti will say more words about this field.